Hi, this is a short version of the presentation that I will make on Thursday in our class this week. This presentation addresses the design of a very basic CPU, and we will go through the architecture, then a test bench, and finally a simulation to show its operation in practice. After watching this presentation, I hope that you will be able to design the data path for a simple CPU, also to specify an instruction-specific instruction set using a set of ASMD charts, one for each instruction. And then finally all we have to do is to merge the ASMD charts into a complete CPU control path ASMD chart. Let's start by looking at what could be the minimal possible architecture for a CPU. Well, we need an instruction register, and the reason is that we will have one single bus to transfer data and instruction opcodes from the memory into the CPU. And so when we fetch an instruction opcode and bring it inside the CPU, we need one register where to hold this information, or otherwise, as the content of the data bus changes, we would lose the information about which instruction is being executed. So the instruction register will latch the information concerning the current instruction being executed, and its outputs containing the instruction opcode will be taken into the instruction decode and execution control unit, which in fact is the control path for this FSMD, which represents the CPU architecture. Besides these two blocks, we will need a program counter, which is the block generating the addresses to the memory. For each instruction that is executed, we will normally increment the program counter. I say normally because if we jump into a different address, then the program counter is not incremented. And finally, we need some sort of data register, or otherwise this architecture wouldn't do anything at all. So we have 4 blocks present here, and we couldn't do without any of these 4 blocks. That is why I call this a minimal CPU architecture. I've also represented a small memory here, where you can see some instructions stored. The first of which is the load register with memory. This instruction, what it does is that it simply fetches the second byte into the data register. So this instruction actually occupies 2 memory bytes. The first one is the instruction opcode, and the second one is the data that we want to load into the data register. Then I'm considering an increment register instruction, and then finally a jump instruction. And of course, jump will also be a multi-byte instruction. In this case, if we assume that the data bus has the same width as the address bus, that is to say 1 byte, then the jump instruction will take 2 bytes. Apart from this, I will also consider a halt instruction to stop the program execution. But let's look at the load register from memory instruction, for example. How do we design this instruction? Well, we have to draw an ASMD chart that represents the sequence of operations that will have to take place as this instruction is being executed. Now, the first thing that we have to do, which is common to every instruction, is to load the instruction register with the content of the data bus. And I'm assuming that the data bus will contain the operation code for this instruction at this moment. At the same time, we will have to say increment the program counter so that the data bus will receive either the next byte if this instruction, which is the case here because the load register with the value from memory takes 2 bytes, or if it was a single byte instruction, incrementing the program counter would bring the next opcode into the data bus. Now, once this state is executed, we move to a second state where we will check if this is the opcode for load register with memory. If it is not, so if the result of this decision box is false, then we will have to check for other opcodes. This might be a different instruction. But if this is true, then we will have loaded the opcode for load register with memory, and in that case we have to load the content of the data register with what is present in the data bus. And of course we will again need to increment the program counter so that we will point to the next opcode to be executed and then jump to the beginning. Now, if this was the jump instruction, for example, the first state would be the same. As I just said, we need to load the instruction register with the instruction opcode and then to increment the data bus. But then, if we ask if the current opcode represents the jump instruction, and if this is true, then what we have to do is to load the program counter directly from the data bus. So instead of incrementing the program counter, we will load it with what comes from the data bus. If you look at the control and data path architecture, you will see that the program counter can be loaded directly from the data bus. And this means that we will just jump into a different memory area. And of course, upon doing so, we will just go to the beginning to execute the next instruction. What about halt? Well, the halt instruction starts by the same operations in the initial state, and then what it does is that if this is the halt opcode, then we simply stay in this state. So the CPU would be locked into this state and no further instructions would be executed. I haven't represented here the ASMD chart for the increment register instruction. I will leave that up to you to practice. Now, if we put these three ASMD charts together, we get the ASMD chart for the full CPU control path. And this is actually the ASMD chart for the control path of the FSMD that implements this CPU. You will notice that what I've done is that I've just merged all state 1 representations into one single representation. So if this is jump, we will load the program counter from the data bus. If not, we will see if it is the load register from memory instruction. If it is, we will take the value from memory into the data register and increment the program counter. If it is not, we check if it is the halt instruction, and finally, if it is false as well, then it's because it's an illegal opcode, and we'll just ignore it by going back to the beginning and considering that the next memory position may contain a valid opcode. If we want to represent the full CPU with the memory, we could do so as shown in this slide, where you see that the address bus coming from the program counter drives the memory, and the memory outputs drive the data bus that goes back to the CPU. So at the top level, if we were in Vivado, we would have this representation. And what I propose now is that we go indeed into Vivado and carry out the project. I have a session, I will open one session to the virtual machine where I have Vivado running. And we will start by going into the canvas page where we have the files for this project available. You will see that in this canvas page you have a link for the source files to the basic CPU with ROM. This is just to speed up the process. So I'm providing you with the VHDL description files for the CPU, the memory, the top level design, and the test bench. So if you click in this link and you download these 4 files, you can then go to the Windows Explorer. I think we can now minimize the Chrome window, uncompress this file, and the four VHDL files will now be available, in this case in the Downloads folder. So let's go to Vivado and create a project, and let's call this project Basic CPU for SHC 4300, and let's create this project subdirectory in the directory where I keep my designs. So I'm not going to specify sources at this time. I have to indicate what board I am using. In this case, it's the Xilinx board, the Basis 3 board. So everything is correct. I can click on Finish, and the project is being initialized. Here it is. If you check the settings, you will see, you can see that everything is as expected. We are using VHDL as the target language, and the Basis 3 board is our target board, so everything is okay. Let's start by adding sources, and in this case the design sources to our project. We'll select Add Files, and that should be available in the Downloads folder. And here we have the CPU, the ROM, and the top-level file. The other one is the test bench, which I will leave for later. So I'm selecting the Copy Sources into Project option, and we are ready to finish specifying what files we want to have here. And there they are, our CPU file. If you maximize it, you can see that I've defined the operation codes for the load register with memory, which in my case I've selected as being A0 in hexadecimal, increment R, which is B0, jump to a different memory position, that's C0, and halt, which I've selected to be FF. The rest is pretty much standard. This is the state register code section, which is, as always, for a sequential design, and then have the next state and more outputs section, and this is what defines the control path for our FSMD. So you can see here that this is simply state after state. So when the state is all 0, and at this point you should compare this with what you see in this slide number 8. For state all 0, we load the instruction register and increment the program counter. And here it is how you do it. You load the instruction register and you increment the program counter. Notice that I've defined these signals as unsigned because I want to increment the program counter, so this couldn't be a standard logic vector. What this means is that we will have to convert it, do a typecasting operation to convert it to standard logic vector when we bring it to the output pins of the CPU. Now, on the other hand, if we are in state 1, we will check for this sequence. So in state 1, what we do is we check if the content of the instruction register is load register with memory. If that is the case, we will just load the data register with the value coming from the data bus. We will increment the program counter and move on to state 0 again. So load the data register and increment the program counter. That's what you see specified here for this instruction. Likewise, if this is increment, then what we do is simply increment the data register and move on to state all 0. And finally, if this is jump, then what we do is we load the program counter with what is coming from the data bus, and we go to state 0. Well, actually, we still have the halt opcode, and in that case, we don't do anything. We stay here as what was said earlier. If nothing of this is true, then it's an illegal opcode, and we just go back to state 0. So this is what concerns the CPU file. Now, the other files are pretty standard. The ROM design file is just an adaptation of what you have in the Pongshu's book. In this case, I've chosen to load this sequence of opcodes into the initial positions of the ROM. So in the case of this design, we are considering that the first instruction stored in the ROM is the opcode for load register with the value coming from memory. And the value coming from memory in this case would be 55 hexadecimal. So this first instruction, what it does is it loads the data register with 55 in hexadecimal. Then the following instruction is increment data register, which I've just used it twice. And then jump to a different memory location farther away, but since all the other positions have, well, actually, it will jump to a different position, but it may find 0, 0, and eventually it will end up by finding all ones and then stop there. Let's see how it happens with this file. So we can start, and of course we have the top level design. The top level design just brings together instantiates our two components, the CPU and the memory, as you see here. So let's check that there are no errors. So let's save project, yes. Hopefully there will not be any errors. It's running the synthesizer at this moment, as you see this circle turning there on the upper right corner. And if everything is okay, we should have no errors, and then we will be ready to add the test bench to our project, which I hope to be able to do in a minute. Still running the synthesizer. Bear with me. You should actually do this by yourselves, since you have the files available in Canvas. Everything is okay, so synthesis was successfully completed. Let's add a test bench, in this case, add or create simulation sources. And we'll add it from the downloads folder. That will be the test bench. Copy this source file into the project, very well, finish. And now we will have the simulation source here. And if we open this file, you can see that our test bench is a very simple test bench. It's just, there's one process which generates the system clock. Then there's another process that just resets the whole architecture and for 2 clock periods, and then I just drive 50 clock pulses. Since the program is stored in memory, all I have to do is to drive clock pulses to this architecture, and it will fetch the instruction opcodes from memory, execute them, go again to the memory, and so on. So let's run the simulation for this test bench. Again, we have to wait a bit. And then we will have to add the signals as we wish to observe them. Here it is. Don't think we need this signal here, so we can delete it. But let's create exactly the same conditions that you will see in the slide. So we have the state register and then the program counter. We have the state register. Actually we can select them all the way. The state register, program counter, instruction register, and data register. Same sequence as in here. So let's add them to our design. And let's maximize this window. Actually, before that, let's just run for, well, 10 microseconds will be enough, I guess. Go back to the beginning, run for 10 microseconds, and then we can expand the simulation window. Bring everything within view. Let's place ourselves at the beginning, zoom in, and here's the information, which supposedly will be the same that I have previously copied into the slides. You see, this is the reset pulse at the beginning. Then we start by loading the instruction register with the first opcode, and the first opcode was A0. That's for load register from memory with 5.5. So the content of the data register will be loaded with 5.5, as we see here. And then we will move on to the next instruction, which is increment the data register, and this instruction is executed twice. So you see that the state goes from 0 to 1, 0 to 1, and then after a while we end up by jumping into the C0 address. C0 is the jump opcode, and the jump opcode will take our program counter to, let's see where, 08. Why is it taking us to 08? Let's check that in the ROM. So the ROM is here. Let's see what is here. Yeah, we will jump into address 7, which is what you see in this case, address 7. So if we go back to our simulation window, you see that address 7 was indeed loaded into the program counter. So instead of incrementing, going from 5 to 6, it was loaded with 7. Then it will be incremented, but it will not leave from state all1 anymore, since that was the halt instruction that was found. So let's go back to the presentation slides. Here you see the top level as it was shown if we went through the elaborate stage in Vivado. Then you have the test bench, which was used for simulation, and the simulation results that I have just shown you with the instructions that were executed. Now, if you want to go further by yourself, I suggest that you think about using RAM instead of ROM and add an instruction that writes into the memory, since the read-write memory will enable you to take content from the data register into the memory. You can also enhance the CPU architecture to support arithmetic instructions, for example, to add, subtract, or multiply. How would you change the CPU architecture in order to support two different memories, one for code and one for data, instead of one single memory for both? Well, any other thing actually that you can figure out by yourself. But first and foremost, what I recommend is that you repeat this exercise yourself by going into the Canvas page, downloading the VHDL files, going through them, making sure that you understand them, executing, synthesizing, simulating, and making sure that everything works in your case as well. Thanks for your attention.